Welcome. This is the first CSE lecture that we're going to have. So to begin, my name is Jeremy Feich. I'm a postdoc at U of T. I'm the manager of the CSE. We're going to start today. First, I'm going to give some opening remarks. I'm going to kind of introduce what the CSE is, introduce all the people that are part of it, and then I'll introduce our speaker. Well, actually, first, I'm going to give you just an overview of the events that we have coming up. We have an educational mission, and we want to have some events that we're organizing. It'd be great if you could all come to them. And then I'll introduce our speaker, Jeremy. He's the only other person on camera that you should be able to see. And yeah, let's get started. Okay, so first, the CSE, what does it stand for? It stands for the Center for Climate Science and Engineering. The CSE, it's a research and education center it's part of the civil engineering department at U of T, and it started in 2019. It's made up of a multidisciplinary team of faculty members, so I think there are about 7 faculty members, and each of them are from a little bit different of a discipline, civil engineering or related to physics, so climate science and engineering there. And the areas that are covered include, as I said a second ago, climate science, but on top of it, transportation, structural analysis, building science, life cycle analysis, and health and process safety. So that's what the CSE is kind of all about. It's just the interdisciplinary faculty at U of T that are looking into climate science and engineering. Okay. So here's the team. As you can see, there are, use that little pointer tool. So this is the center director, Oya Mercan. And then on top of that, there are 6 other faculty listed here. So Marianne Hatzapalu, Paul Kushner, Graham Norvell, Daniel Posen, Karen Smith, Marianne Tucci. Those are all the faculty members. And then myself, I'm Jamie Feich, and I'm the manager. I am not a faculty member. But I do my best to manage the best I can. As I said before, we have some upcoming events. There are going to be, we currently have 3 more scheduled lectures that the speakers are already confirmed for that are going to be coming up. They're about 1 a month, but there's the holiday break, so in December there's not going to be an event, but we have a couple more lectures that will be similar today in format. The closest coming up one is going to be November 11th, and that's going to be a speaker named Cameron Thompson, and he's an associate principal from Arup. And the general topic, it's not fully confirmed, but the general topic is going to be the development of energy master plans and looking at how you can take climate change into account with those. Then the next one's going to be in January 2021 from Professor Lakshmi Shushama from McGill University, thinking about, well, her general focus is on climate change and sustainability in engineering and design. And then after that, there's going to be one in February that's already planned, and that's going to be from Mark Couture. He's the Director of Sustainability and Operations Services at U of T, and he's going to talk about the U of T energy standard, how you can build different standards based upon local standards for, it's more policy and retrofit influence based. Anyway, so we have 3 upcoming lectures that we already have planned. And on top of these lectures, we also have not sure what happened to the formatting here. I think it got a little changed when I uploaded it to the Blackboard software here. We have a few upcoming workshops. So these workshops are actually led by the CSE faculty members, and they're going to consist of a 1-hour lecture followed by a 1-hour kind of class activity. Then there's going to be a 30-minute follow-up lecture and then 30-minute of just discussion that would go on. The first 3 of these that are planned, so in November, so about a month from now, is going to be the introduction to the course and a case study on wind loading. That's going to be by Professor Oya Mercan and Paul Kushner. The next one is going to be in January, so again, in the new year, and that's going to be focused on global climate modeling and regional downscaling, and that's going to be from Professor Paul and Professor Karen Smith. And then the last one that's on this list, we have other ones planned, but the last one on this list is in February, and that's going to be the impact of changing climate on building performance by Professor Marianne Tucci. And these ones, unlike the lectures, the workshops are only for U of T students. So the lectures are open to anyone who wants to join. These workshops are for the U of T undergrad and graduates. So just if you're interested, we will be sending out communications about them, and we encourage you to participate. So that's pretty much all for me. Now I just want to introduce our first inaugural CSE lecture series speaker, Dr. Jeremy Feich. He works at the Canadian Centre for Climate Services. He received Ph.D. from the Victoria University of Wellington in New Zealand. He then completed a postdoc and staff research at Los Alamos National Laboratory, where he focused on the development of methods for coupling ice sheets into climate models and researching paleoclimate questions, natural variability, noise, emergence of climate signals, and cumulative carbon emission scenarios. Currently, he works as the coordinator with the Data Products Office at the Canadian Centre for Climate Services within Environment and Climate Change Canada. In his role, he interfaces with the engineering sector across several engineering disciplines. He is currently an adjunct professor at the Department of Geography at Simon Fraser University and the Department of Atmospheric and Oceanic Sciences at Colorado University at Boulder. In November, he'll be taking his professional practices to gain his professional geoscientist certification with engineers and geoscientists of BC. So that's all for me, and please enjoy the presentation from Jeremy.
Thank you very much. So I'm going to do a quick screen share here. And there we go. Now, how does that look? Can folks see the presentation?
Yeah, looks good to me, Jeremy.
Awesome. Okay, cool. Well, why don't I get rolling? Thanks, first of all, Jamie and everyone at the center for hosting me and actually hosting this lecture series, and more generally, focusing on the intersection of climate change and engineering. I think it's just a super important place to work. And so when I actually first heard that the center was up and running, it was really exciting. I think it's a good topic, so congratulations on stepping into a really important topic. So I'm going to talk today about some I've learned and something that I'm kind of somewhat passionate about, which is climate change risk, how to frame climate change in terms of risk, and then how engineers can have a really important role in reducing climate change risk. Just to double check before I get rolling, everybody saw that slide change, and it's I'm still online here.
Yeah.
Okay, sounds good. Sorry, I lost my sight of all of you, so I just want to make sure I'm not talking into a vacuum here. These are I think the three general questions that I want to try and circle around and try and formulate maybe some answers to in the course of the next hour or so. And the questions are, what exactly do we mean when we're talking about climate change risk? What does that term mean? How can we bring climate change in the context of risk into engineering work that engineers do? And then kind of the question, like, why should we even bother doing all this thinking and work to think about climate change and engineering? So these are the really general questions that you'll find we're orbiting around in the next hour or so. Those are climate stripes for Toronto, and so it's a great visual that I like to put up just off the bat to highlight the really kind of visceral nature of even ongoing climate change today. Jamie, thanks for the introduction. And sort of background of who I am. I can reiterate this really briefly, and I think more in the context not of who I am, but some of the experiences I've had and how they relate to bridging climate change and engineering, which I think is a really important topic. So I would self-identify most as a climate geek more than anything else, and so I spent a fair bit of time going through grad school, getting really into climate research and climate modeling, which are really cool tools, and then doing some postdoc and science work in a variety of places. Victoria out here in BC, New Zealand, down the States, in New Mexico at Los Alamos National Lab, which is a fascinating place to do climate work because it's also the birthplace of the atomic bomb, and so you get to do climate modeling surrounded by armored vehicles and gates and security guards. It's a fascinating place, but there's big computers there, which makes it a wonderful place to do climate modeling, which is why there's a great crew of climate modelers there. As Jeremy, as you mentioned, I'm adjunct prof at SFU and CU, both places of which are hosting very different but very groundbreaking styles of climate research and attempts to apply that research to the real world. So it's great to interact with folks there. That's I kind of identify most as a climate geek more than anything else, but I also spent some time immersed in the engineering sector. So on the other side of the spectrum, I worked at engineering, Associated Engineering, which is a more Western focused civil engineering company, kind of mid-sized company here in Canada, doing lots of water resource work, linear infrastructure, buildings design. So lots of really great civil engineering, and that was trial by fire for me in learning how engineers work and how to try and bring climate change into the engineering world through my role as a climate specialist there. And also, as Jay mentioned, I'm working now to become certified, not as an engineer, thank God, but as a geoscientist through EGBC, which is the BC provincial chapter of Engineers Canada. So through that, I'm learning more about the background behind professional engineering and geoscience, which has, I think, a big bearing when it comes to climate change. And I'll touch on that later in the talk. And so those are some of my past experiences. My present experience is really working to bridge the gap between climate research and the real world, to call it that, which is the bridge called climate services. And I'm working in climate services at the Canadian Centre for Climate Services at Environment Change Canada, where I sit in the data products office, working to bring data and information and communicate that in a way that makes sense to people on the ground floor of making decisions, the important decisions out there in the world. And a lot of that does circle back to the engineering sector. So it's a great place to play and try and bridge these experiences that I've had and make them useful and relevant to Canadians. That's who I am in a nutshell. And maybe that gives you a sense of, what I've learned and maybe a sense of, where I'm still trying to learn. I'm always trying to learn climate science. I'm always trying to learn engineering, and then definitely trying to learn how to bridge that gap. So it's an evolving topic for me, and I'm happy to share some of my thoughts on it in the next little while. I'll give a brief just review and summary of the Canadian Centre for Climate Services, a really unique organization hosted by, like I said, Environment and Climate Change Canada, Government of Canada. There's some really interesting resources that the Canadian Centre for Climate Services provides. Maybe off the bat, there's a support desk. You can, no joke, call the number and have someone answer and help you with your climate question. It's a really unique service that is provided to the public. The number is down there on the screen. There's an email. You can also get in contact with us. And then we host a website, actually a series of websites that allow access to a wide range of climate data sets through different climate portals, lots of resources, lots of tips and tricks for training and user engagement. And we're always happy as well to work on developing new information and data products that speak to providing Canadians with good information for their decision support as they bring climate change into their day-to-day decision making. We host climatedata.ca. It's a great website that you can go and explore lots of different indices of climate change. I will also note specifically that you can also now, as of fairly recently, do your own analyses on climatedata.ca through custom indice creation and things like that. So I encourage folks to go and check out climatedata.ca. We play a role as well in the Climate Atlas of Canada, another fantastic website, and development of kind of more power tools for evaluating and analyzing climate change, like the AVIX tool. We work closely with regional partners, Fyke on the West Coast, Paranos in Quebec, and his other partners in development as we speak. So the constellation of climate service providers in Canada is growing. And the last highlight here is just the climatedata.ca website. We host climate data you can explore in terms of the data itself and a bunch of computed temperature precipitation-based indices. for past climate, future climate. We also have straight observational data, and like I mentioned, a really unique and powerful aspect of the tool is that you can go in and actually design your own custom data analyses. And after a couple minutes to a couple hours, depending on what you ask for, you'll get an email saying your analysis is ready, and you can go and grab it. So it's a great service that I encourage folks to explore and try out. Okay, let's jump in here. I'm going to start this talk with some, I call them climate change basics, and I think I'm sure a lot of people in this room don't need this kind of message, but I think it's a great thing to start with anyway, because it frames thinking about climate change as risk. So we can get spun up on the basics together in a couple minutes here. So this is a great graphic I love. It's just beautiful. It's a map of the world every year from 1850 to 2018, I believe, is the last version of this. Temperature anomaly at each point, annual average temperature anomaly. And you can really visually see climate change emerging, especially after around the 1960s, 1970s, in the form of more red on each map of the world. It's also great to see how our knowledge has evolved over time. If you look to the 1800s, the information we had about the world was fairly scant because it was mostly picked up through ships with thermometers traveling on trade routes and some key places on continents, whereas now we have satellite coverage and fantastic availability of information to our understanding of climate change. Climate is changing. We can look at it at maps. We can look at it evolving over time in these fantastic circle diagrams, I guess you call them, looking at change over the seasons per year. We see it's getting warmer, but there's also variability, right? So sometimes a point gets colder than average and warmer than average, but on the whole, the system is changing in a way that is very consistent with physical understanding, right? And this is the parallel plot of CO2 concentrations increasing over time, year after year. And left hand is the reason, right hand is changing. These are very coordinated plots. This is data over time. The understanding of the basics of why this is happening is really not all that new. In fact, it's almost 200 years old at this point. Give it another 4 years. This is science that's well understood, and the basis of what we call climate change science, let's say, is nothing new. It's well-established physics, and that's what we're building on with development of more and more sophisticated models that take that understanding to different levels of sophistication and specificity. That's the picture, globally, and we can zoom in on how climate change is impacting us here in Canada and has impacted us here in Canada. This is a animation of temperature change over time at points where we have good long records of this temperature change, and the picture is pretty well known. Lots of variability. Sometimes we have cold years, sometimes we have warm years, but on the whole, we see more and more red emerging in this plot. This is one of the big signals of climate change is warming temperatures over time. Temperature is one thing. Of course, there's lots of other metrics of climate change. Precipitation is another. These are a series of plots from the 2019 Canada's Changing Climate Report, showing that even in the observed record, we have noticeable increases in average precipitation over a lot of the country, especially in the north. And then if you average that change up over time across Canada, we're trending towards more and more precipitation on an annual basis. So there are some certainly measures of precipitation and the hydrologic cycle that we have some pretty good confidence in. But it's important to note that there's still lots of uncertainty, right, in our understanding of important aspects of the system and their change over time. So the bottom right plot is a plot of changes in stream flow volume, over time. And the interesting thing here is there's lots of green dots on this plot, which means that there's still not a measurable signal of change in lots of places as far as stream flow goes. And so there's lots of uncertainty and noise in the system still that we're working through and watching signals emerge sort of in real time. So this is sort of the boilerplate summary of climate change as we've observed it. Of course, people are very interested in how climate change is going to change in the future. And to speak to that, we turn in large part to climate models. And we can run these climate models under different scenarios of future climate change and build up a picture of how climate will look like in coming decades and even all the way out to the end of the 21st century and beyond. This is a classic plot again from Canada's Changing Climate Report, showing average Canadian temperature change in the past in the gray and black, and projected into the future under a few different climate scenarios in red and blue. And it's interesting to think about what these scenarios mean, especially as we start thinking about the context of how we respond to climate change as a global society. So on one hand, we can think of really kind of the worst case bookend of climate change, which is RCP 8.5, Representative Concentration Pathway 8.5, which is really defined as a scenario of comparatively high greenhouse gas emissions. So this is kind of the worst case amount of change that we expect to see at this point through the 21st century. And there's a lot of change there. It's sort of the upper bookend of what we should expect to have to respond to. On the other hand, there's RCP 2.6, which is sort of like we all go out tomorrow and buy a Tesla, no one flies, and everyone becomes vegetarian. That's the way I put it. It's a very optimistic scenario, officially described as a scenario with the most stringent climate policy. So this is sort of the lower bookend of change that we as a Canadian and global society can probably expect to have to deal with. And that's still a significant amount of change relative to what we've experienced in the past and what our engineered infrastructure has experienced in the past. This generic plot is a nice way to sort of conceptualize the different ways that we, as a society, individuals and organizations can and will have to respond to climate change. So we can consider really simply just the baseline of past climate and two measures of future climate, lower end and higher end of these bookend type scenarios. The way we deal with this is through generally two types of approaches. On one hand, we have climate mitigation, which generally refers to actions to reduce specifically carbon emissions, or in particular carbon emissions, but more generally reduce our actions that are causing climate change in the first place. So climate mitigation is one very important basket of actions that we can undertake and are undertaking now to try and push us down from the red line more towards the blue line, so that climate mitigation takes us away from RCP 8.5 towards RCP 2.6. The other basket of actions, if you want to call it that, is climate adaptation. And these actions recognize the fact that even under the most optimistic scenarios, there's still going to be, and already is, a lot of change coming down the pipeline for us to deal with, even if we follow the best case scenario. Okay, so climate adaptation actions are those that are meant to reduce climate change risks. So they reduce the amount of risk that we experience and make ourselves and our organizations and our communities and our society more resilient to the climate change, which some portion of which is essentially unavoidable. The key point of this is identifying climate change risks and characterizing climate change risks in a way that allows effective decisions around actions to be undertaken. Right? And so climate change risks become a really key point in understanding how we adapt to climate change. And this is the theme and the topic that the rest of this talk will be kind of focused on. So we're going to be talking about climate change risks in context of climate adaptation. Climate mitigation, super important, and I'm almost certain that will be the topic of future lectures here. But right now we're going to focus on climate adaptation and how climate risk plays into that climate adaptation conversation. Everyone still there? Great. Awesome. Okay. Let's talk about climate change risk because I think it's a really important topic, one that I feel is just key to the conversation, and so I'm hoping I can share that with you and encourage you to dig into the concept of risk and how it relates to climate change a little more on your own. I'll tell you what I know. What is climate change risk? Well, maybe we can back up a bit and think more generally about the definition of risk. There's two definitions of risks that I'm showing here, and they come from each side of the bridge, the engineering side, engineering discipline, and really the climate science, the climate change side. First quote is from Engineers Canada. Risk is defined by Engineers Canada as the possibility of injury, as in sort of personal injury, loss, or environmental injury created by a hazard. UNIPCC, I believe this is from Working Group 2, defines risk as the potential for consequences where something of value is at stake and where the outcome is uncertain. Now, what I think is just fantastic about these two quotes is that they're saying essentially the exact same thing, but they're being said by people on different sides of this divide between engineering and climate change and climate science. So the fact that we have a really nice common definition of a term, not just any term, but a term that's really fundamentally important to both of these disciplines, means that it's a great avenue to facilitate conversation using a common language between engineers and on one side and climate scientists and the climate change community on the other side. So maybe this is the most important slide of this talk, because it really highlights that risk is a great common language that allows engineers and climate geeks to interact really effectively with each other using a language that they both understand off the bat. So it's fantastic. Risk is great for that reason alone. Let's think a little bit more then about what risk actually is. And there's a universe of risk assessment and risk management methods and textbooks and learning out there. And it's really interesting stuff. And I encourage folks to get into it because I think it's important. This is one classic definition of risk that is applied in a lot of places. And so we can explain more about the definition of risk. Risk can be defined as product of the likelihood of some event, like basically multiplied by the consequence of that event if it occurred. So risk equals likelihood multiplied by consequence. Risk is the likelihood. Risk is the product of likelihood and consequence. There's different words that you'll encounter in risk terminology and semantics. Likelihood is sometimes called probability or frequency. Consequence is sometimes called things like severity or sensitivity or vulnerability plus exposure, and there's probably other terms out there, but when you boil it down, these all sort of mean the same thing. They are how likely is an event to occur and how bad would that event be if it occurred. And so if you multiply those two factors together using some quantitative or qualitative measure of multiplication, you end up with a measure of risk, and you can represent that measure of risk on a risk matrix, which is the colorful set of squares over on the left-hand side. If you have a low likelihood and a low consequence value, then you end up in the green area, which is low risk, very low risk. And conversely, if you have a very consequential event that has a high likelihood of occurring, then you have a high risk event. That gets you popped up into the red section up in the top right. So let's play with some events on this risk matrix and see what we end up with. Let's start out with a Comet Impact. Very intense event, very consequential event. So we know that when a comet strikes the Earth, it causes lots of really big and bad consequences. But we also know that the likelihood on sort of let's say a day-by-day or year-by-year basis of a comet hitting the Earth is pretty low. Right? And so if you multiply the likelihood of a comet impact by a consequence of a comet impact, you end up actually in sort of a low risk area. And that makes intuitive sense because I don't think many people here walk out their door every morning extremely concerned about getting hit by a comet. It's a low risk event, even though the consequence of that would be super high if it actually happened. Think of another event, a mosquito bite. Like at least in Canada, and lots of places in Canada, the likelihood of mosquito bite is really high, especially in spring, like many mosquito bites per day maybe. But in general, the consequence of a mosquito bite is pretty low. There's some exceptions. There's not zero consequences from a mosquito bite because you may just possibly get West Nile. But in general, the consequence of a bite is pretty low. And so a mosquito bite gets low risk rating. And so it's kind of counterintuitive that a mosquito bite has the same risk level as a comet strike. But it makes intuitive sense. When I step out the door in the morning, I'm not horribly concerned about getting bit by a mosquito, about to the same level as I'm not horribly concerned about being hit by a comet. So risk matrix is a great way to sort of contextualize very different types of risk. Here's COVID. COVID is a different story because COVID is relatively likely, to impact individuals on this scale. And it also has pretty high consequences if it does impact you. And so for this reason, when I walk out the door in the morning, I bring a mask. I'm actually treating COVID as medium to a high risk in my day-to-day activities. And so we can place different events on risk matrices and start to understand, our actions and actions we should do address those risks, or at least understand them more. It's important, I think, to note that risk also has a negative or inverse, which is opportunity. And you can reflect that in terms of kind of like a negative consequence scale. This is really important actually in climate change because climate change presents change that can be risky, but also can present change that can be reflected as an opportunity. So if you reflect a risk matrix upside down, then you get sort of like an opportunity matrix. I'm not sure if that's a thing, but we can call it that. And you can start to think about events on an opportunity matrix. This is a great example. This is Adlin Lewis, who in 2020, January 2020, in Brampton won the biggest lottery in Canadian history, $70 million. This was a very high consequence, low likelihood event that he benefited from. As an absolutely pertinent aside, Adlin Lewis is the credit risk manager of Scotiabank in Brampton. So he's well placed to understand this conversation if he was actually here on the line. This is one of my favorite examples of a risk matrix in action. This is a matrix of global risks produced every year by the World Economic Forum as part of their global risks report. And so we can see the format here follows the standard format of a risk matrix. There's impact on one side, which is like consequences, and then there's the likelihood of occurrence on the other axis of this plot, the x-axis. There's a bunch of global risks scattered on this plot, not scattered, placed according to their impact and likelihood ratings according to the World Economic Forum, for a bunch of different families of risks, from environmental through to technological, and you can see that by color. What's fascinating is that climate action failure and extreme weather actually are really clearly and significantly at the top of this pile of risks, both by their likelihood and by their impact. And so it's a nice segue into climate change and climate change risk, but in general, this is a beautiful example of a risk matrix being used to partition and prioritize different risks based on global society. You can look at risk change over time too, and we'll do that when we look at climate change for sure. This is the same information from the 2020 World Economic Forum Global Risks Report, but now it's looking at past reports which come out once per year and looking at how the different risks have evolved over time in terms of their likelihood and impact. And what zero order this shows to me is that over time, economic risks in terms of their likelihood and impact have been kind of supplanted in recent years by worry around environmental and specific climate change risks. And that's shown by the fade from blue as the dominant color down low, especially around 2008, economic collapse. Now it's primary worry at the global scale, according to the World Economic Forum, is now more around environmental risks, including climate change. You can also, and the World Economic Forum does, organize risks by their linkages to other risks. And this is a neat way to show that the world is indeed very interconnected. Climate action failure is the top risk on a pile, according to the WEF. And it's very interesting to note where links to in terms of other risks. It links to food crises, global governance failure. From the engineering perspective, it links to failure of urban planning, water crises, and a bunch of other risk baskets that have, a real clear engineering flavor to them. Okay, I'm going to do one more check-in. Is everybody still there? Great. Okay, so that's a sort of a general overview, or a general review of at least my understanding of risk. Risk is a great way to understand concerns about what could impact you, and then start to think about ways to respond to those concerns. So risk is a great language to use in general. Let's dig in now a bit more how we think about how we can think about climate change in the context of risk, and specifically in the context of engineering work. Okay, so we're going to put this risk matrix back up, and what we're going to do for the next couple of slides is kind of play around with this risk matrix and see how we can start to represent climate change in terms of moving around this matrix, or communicating climate change in terms of risk. We'll do that with a couple case studies. The one that I think is great is the 2018 Toronto flood. So I'm sure people in the audience there probably experienced some of this flooding firsthand, I imagine. This is a great iconic picture of that flood, showing some emergency management folks running past a whole bunch of engineered infrastructure that is not doing too well because of this flooding event. There's storm sewer systems overflowing. There's a drowned trolley. Lots of buildings probably being flooded through their basements. Hopefully that wasn't close to where those two fellows almost got drowned out of their elevator. This is a very serious event in terms of its consequences. So if I were to place this event on the consequence scale, between a mosquito bite and an asteroid strike, I'd probably place it somewhere about in the middle. So let's put it there for now. What's important here to note is that the consequence scale is a great place to get stakeholder and user and system manager understanding of the damaging impact of particular climate events. So this is really a way that if you were a little more rigorous than I just was, you could start to define, monetary damage and damage to equipment and asset damage because of this type of event. This is where stakeholder input becomes really important. The likelihood scale, on the other hand, is kind of where the climate side of the equation can speak to pretty eloquently. So here is an IDF plot of it's a station in downtown Toronto, it's Toronto Booth Station or something like that. This is pulled from Environment Climate Change Canada, is actually from climatedata.ca. Shameless plug. Get great historical IDF information from climatedata.ca, and plot it up really easily and simply. I did that here, and Get Into Toronto was around a 2-hour event that I believe dumped around 80 mils of rain, if I'm not mistaken. And if you plot that red star on this IDF curve, you end up with something like a 1 in 100 year event. I think it was actually put it more locally, but let's call it a 1 in 100 year for the sake of argument here. So this Toronto flooding event was around 1 in 100 in terms of its likelihood. 1 in 100 year is kind of equivalent to saying there's about a 1% chance per year for this type of thing happening. So you can actually get pretty quantitative with your likelihood statements, and this comes from weather and climate data. So you take the consequence and the likelihood together, and you put a star on the risk matrix map, you can actually end up with a risk statement around this 20 Toronto flood. And that's not to say that it falls here in the low risk category. Again, that's mostly because it was, in principle at least, a relatively rare event. And it kind of matches maybe with intuition. It was a rare event, so a lot of the infrastructure in Toronto wasn't really designed to handle that because it was considered a rare event. It was below the risk threshold for redesigning infrastructure. So this is where the star falls for the present day in terms of a risk value related to the 2018 flooding in Toronto. there's certainly other ways to define the axes and then scaling and stuff, and that's an important conversation to have. But we'll take this as an example for now and run with it, because I want to think about how climate change impacts this picture. Climate change impacts a picture, and you can demonstrate the impact of climate change on this risk matrix in a few different ways. So I'm going to get you to do is keep your eyes on the IDF curves as I move to the next slide, and they're going to shift slightly. Slight shift is actually a big shift, but it's on a logarithmic scale on the y-axis, so it looks pretty small. Keep your eye there, and I'll move it up. What climate change is very likely going to do in Toronto and elsewhere is increase the intensity of a given storm duration and annual exceedance probability. These 2-hour storm, 1 in 100 year 2-hour storm is going to get more intense because of climate change on average. Okay, so what that is going to do, what you can call that, is a change in the consequence. The same 1 in 100 year 2-hour storm is going to be much more consequential for the city of Toronto. There's going to be more storm system overflow. There's going to be more drowned infrastructure. Hopefully there's not going to be loss of life, but of course that's a big consequence. And so the important thing here is you can actually represent climate change as a shift on the risk matrix. We started out at where the star is now. We've shifted that star up to represent climate change through a change in the consequence of a 1 in 100 year storm. So the important takeaway here is that climate change can really be represented by moving your point around on a risk matrix. We go back and think about how climate change can be represented not in the vertical axis of this plot, but in the horizontal axis plot, the likelihood axis of this risk matrix. I'm going to ask you again to keep your eye on that IDF curve down to the lower left, and I'll move forward, but this time I'm going to keep that red star fixed, so it's not going to move up with the plot. When you do that, what that indicates is that intensity storm of 2-hour storm is going to go from about a 1 in 100 year event to about a 1 in 25 year event. I think that, correct me if I'm wrong, I think that goes from 1% to a 4% chance per year, something like that. That's right. So you can reflect climate change not just in the consequence scale, but actually a little bit more intuitively on the likelihood scale. You can say, okay, climate change is going to cause this type of event to occur more frequently on average, and so that's they can reflect climate changes through a shift in the horizontal on the risk matrix. Again, the important thing to note is that you can communicate climate change in terms of changes in risk, specifically changes in risk on risk matrix. That means it's great. You have a method of communicating here. Climate change is exactly equivalent to change in risk, and you can communicate that very well and very clearly, I think, using these standard risk tools and visualization techniques. So climate change can be represented as a change in risk. Climate change is a change in risk. The climate change has, as we all know, lots of uncertainties associated with it in terms of actually pinning down, with absolute precision what climate is going to look like at some point in time in the future. The reason we're not totally certain on that number to 6 decimal places is largely because of 3 sources of uncertainty. There's uncertainty in what humans do in terms of their carbon emissions and other climate influencing factors in the future. That's collectively called forcing uncertainty. It's the difference between RCP 2.6 and RCP 8.6. There's model uncertainty. So for the same carbon emission scenario, for example, you run it with different models and you get slightly different results, sometimes very different results. Same thing as weather models. One weather model tells you something weeks in the future and another tells you something else. And the third source of uncertainty, although it's kind of irreducible, the natural aspect of the world is internal variability. The climate is kind of a noisy system, a chaotic system. And so that necessarily puts a bit of a blur on any projection of future climate change because there's just that natural chaos in the system that we can't really predict far out into the future. So there's these 3 sources of uncertainty. You can kind of reflect them if you're into statistics. Speaking statistically, in terms of some sort of distribution space where the parameter of a particular climate variable, annual mean temperature or stream flow or whatever you want, is really a function at any X and Y location in Canada and time in the future, internal uncertainty, if you want to call it that, and then certainty around models and also forcing. So we can see with some certainty that future climate change parameter X is going to fall within this square, this box, but it gets a bit hazy when we try and exactly pin that down. So this is the uncertainty around future climate change that is really unpalatable when speaking to an engineer who very rarely is not just designing a distribution of billion-dollar bridges, they're building $1 billion bridge, and they need really, in the end, one number. And I can sympathize with that, even as a climate scientist. There's a real challenge there. So how do you communicate this uncertainty in a way that makes sense to the engineer who needs to pin down a value to design to? You can actually do that. You can facilitate that conversation really well using the language of risk and risk management. We can think about that if we go back to the risk matrix. So here's our present day risk level, again, for 2018 Toronto flooding. On one hand, if we choose to go to one corner of that box of uncertainty and choose, let's say, a very insensitive climate model in the RC 2.6 scenario, and we find the coldest year or whatever of 2100, we can get an amount of change that's actually not that big, and that is reflected on the matrix going in the x-axis. There's a small change in likelihood. In other words, a small change in risk. So that's a tangible translation of climate uncertainty into change in risk. On the other hand, of course, if we choose a very sensitive climate model, it's CAN ESM, and we take a top-end emission scenario and we kind of cherry pick that the hottest year that CAN ESM ensembles produce in the year 2100, we can get quite a large amount of change, even for mean annual temperature anomalies relative to the lower end. So we can reflect that as a very big change in risk because it's very much increasing the likelihood of this damaging event. Right, and the point here is that not that the risk matrix and risk management gets rid of that uncertainty, but it allows that uncertainty to be communicated in a common language between the climate science community and the engineering community. What's great is you can then start to facilitate some conversations about what to do with that uncertainty. In other words, what to do with that range of risk. You can talk about, for example, risk thresholds. So the blue star provides a scenario that in which the risk hasn't increased much. Perhaps it hasn't increased past a threshold the designer or the owner or the engineer of the engineered thing in question is worried about. And so they may choose not to change their design at all, but they have to understand that that may reduce costs, but then carrying the risk of under design in the case where climate change actually is greater than, for example, 2.6. On the other hand, if they choose to be very risk averse and design to very large measure change, RCP, for example, that may suggest to them that they want to actually build in increased climate adaptation, climate resilience measures. In other words, build in things to their system that will compensate from the shift to the right in terms of likelihood with a shift down in terms of consequence. They're reducing the consequence of a damaging climate event. For example, building sewers 20% bigger in the city of Toronto. That's an adaptation action that compensates for an increase in likelihood with a decrease in consequence. So you can start to facilitate these really tangible types of conversations if climate change is reflected in terms of risk and risk language. The language of risk and risk management is also a great way to talk about other important subtleties of climate change. For example, subtleties related to the time frame over which the change occurs. Let's take ice jam flooding. This is another case study. We'll take two bridges. On one hand, we have a resource road bridge, maybe around for 10 years, and then it will be decommissioned. It's not a long-term structure, an engineered structure, but it's not a long-term structure. On the other hand, we have the Ditcho Bridge, the first bridge to cross the Mackenzie River, built in 2010, I believe, and it has about 75 to 100 year expected service life. Hugely important bridge. It's the one all-season route to get Yellowknife, I believe, Prior to this, there was a ferry that shut down seasonally every year because of ice jams. So let's think about the risk of the changing risk of ice jams due to climate change. On one hand, a bridge that lasts for 10 years, the risk of ice jams is there, but it's probably not going to change a whole lot because of climate change. It's going to be long gone before a big signal of climate change comes through. So the shift along the likelihood axis in terms of ice jam risk here is relatively small. On the other hand, Ditcho will be here most likely after year 2100. And so it's going to experience a very large magnitude of climate change, including changes to ice jam flooding characteristics on the Mackenzie. And so the risk change in this case might be a whole lot larger. In fact, it might push over the risk threshold, which might mean that adaptation actions and measures would be warranted in this case. So you can talk about time frame in terms of risk, actually. Another important consideration is the initial risk baseline we can take, a wind impact. We can think about the wind impact to this building, which I understand is going to be built in Vancouver this year. Incredible building full of, in my naive eye, very fragile glass panels, which may, even in the present climate, be impacted by strong wind pressures and wind gusts. Now, if climate change increases wind in this location, then there's a reasonable likelihood that the increase in wind will push past the risk threshold for this building, such that in the design of it, they may want to consider climate adaptation actions. We contrast that with a bunker. This is in Kansas somewhere, but let's pretend it's in Vancouver. This bunker is, at the present point in time, almost completely impervious to wind risk. And even if wind increased by a factor of 10 in this location, in terms of gusts or pressures, however you want to measure it, the risk would still be small, right? Because the consequence of a wind gust to this concrete bunker is very low. So you can talk about risk baselines. You can talk about vulnerability, the base vulnerability of infrastructure to climate impacts really effectively, again, using the concept of risk and the language of risk management. The final, but I'm sure not the only one, subtlety can be talked about in terms of risk is the direction of climate change or reflected in risk, the direction of risk change. There's a car being charged in the winter. Electric cars don't, as I understand it, run very well in cold weather. So it's a good thing that it's going to get warmer. That reduces the risk of motorists being stranded on the side of the road because they ran out of batteries. It also reduces risks to the underlying transportation infrastructure. So that's actually a reduction of risk. That's an opportunity climate change brings. On the other hand, increasing temperatures don't bode well for old beer cars overheating on the side of the road. So the same direction of impact actually causes an increase in risk depending on your automobile of choice. So the direction of risk change can be, the direction of climate change can be reflected pretty accurately in terms of the direction of risk change. In some cases, it actually goes in the other direction, the positive direction. All right, great. So hopefully, I'm convincing everyone on this call that risk is a fantastic language, not to solve the problem of climate change, but to communicate it in a way that bridges the gap between climate change, climate science, and the engineering profession. Conceptually great. How do you actually undertake a climate change risk assessment in some sort of practical sense? And we can think about that using a great case study. This is the Ash Bridges wastewater treatment plant the city of Toronto operates. This is as I believe, an increased combined storm sewer treatment system. It treats waste from about 1.4 million people. I did the calculation. Hopefully, I think it's right. It processes about a cubic kilometer of waste every 3 years. This is a major facility. It's now undergoing a $1 billion upgrade. It's a major piece of engineered infrastructure. So let's say we were contracted to do a climate change risk assessment for this facility. How would we even start that process? One very big benefit of engineering philosophy and thinking is that it's a methodical style of thinking, and that applies really well to undertaking a risk assessment of this type of thing, a climate change risk assessment. Our step is to break this big monster facility into its components. We can start to think about that. Let's take just one component of this overall facility, which itself you could break into probably 100 or 1,000 subcomponents if you really wanted to. But let's just treat this as one component of this broader facility for the sake of discussion. So first step is breaking the thing into its parts, into its material parts, and analyzing those in some isolation, just to avoid being overwhelmed by scope. How do we start to think about what we want to look at for this one component? Well, the very best place to start is just to take a site visit to the facility, or take a visit to the engineering design if this is a facility yet to be built, and do that visit in close coordination with the operator of the facility, who has hands-on knowledge of how the thing works, or the designer of the facility if it's in the process to build. And the number one question you can ask right off the bat, and this was a question that I learned from a great mentor of mine in the risk assessment world, is what keeps you up at night today with respect to your facility that you're operating or designing? What are the environmental vulnerabilities that today keep you awake and worried at night? And that one question will unleash typically a torrent of comments that you can immediately hang your hat on from a climate change risk assessment and risk management perspective. So here's a picture of some climate change risk assessors, a risk assessment team of a climate scientist, an engineer, and a risk manager coming in and talking to the operations manager of this component, the overall Ashbridges facility. And the operator says, well, wind, heat waves, coastal flooding, these are all things that today keep me up at night. And these are things that may change in terms of the risk in the future. So these are great aspects to include in a risk assessment of this facility. One thing that's missed in that conversation, can be missed, are risks that are zero today but may emerge in the future due to climate change. And so that requires some creative thinking that maybe falls outside this very sort of applied conversation with manager or chief or designer of the component. That conversation is a key aspect to getting off the road, getting off the ground when it comes to doing a risk assessment of this piece of the puzzle. Now, the puzzle has many pieces, and this one has many, many pieces. This is a massive facility. Hopefully you have some budget in your risk assessment. But you can repeat the process, essentially, for all these different components of the system that you're looking at. And so we can go from parking lots to storage lagoons across the board here, and repeat this interaction with the main operator, the main designer, to learn about kind of pains they're feeling now or they expect to feel right off the bat, and then using that as a basis to start a dive into future risks. If you do that, you can actually end up with kind of like a matrix of matrices. Where on one axis, you have the system components. So on the x-axis here, you have all the different components of your system. And on the y-axis, you have all the different climate impacts that were recognized in the course of surveying the system in your field visits or your blueprint visits, let's say. And so you end up with this really comprehensive and complete list matrix of risk matrices that if you did every one in perfect detail, you would have just an absolutely perfect characterization of changing risks across all the possibilities and combinations of climate impacts and system components. That is a ton if you want to do that with engineering detail, and that's why initial high-level screenings are really key in making this a manageable workflow. What high-level screening is just a quick, even qualitative scan to assess from a basic sanity point of view whether climate impact really has interactions with the system for a particular like XY location on this matrix. And when you do that, you can pretty quickly narrow down things that don't matter and remove them from any further analysis. Typically, these are combinations of system components and impacts that fall on like deep into the green component of the risk matrix. They're really low risk, and so there's very low chance of them emerging as a serious risk down the road. You do that high-level screening efficiently and quickly, even qualitatively, and you end up with that looks a little more manageable, and it becomes even more manageable when you try and identify the system components that seem to be very vulnerable to a bunch of different climate impacts, or conversely, climate impacts which seem to impact a whole bunch of different system components. When you do that, you can narrow it down and really start to prioritize your time and budget to focus your analysis on the things that matter most for the system in question, in this case, the Ash Bridges wastewater treatment plant. These are places where you dig into more detail, touch the other ones if you can, and you can more or less discard from deep analysis all the things that seem to be low risk right off the bat. And so there's a great way to boil and prioritize the work down to something that actually is manageable, even though you're faced with what seems at first glance to be a pretty unmanageable problem of identifying climate risk to a giant facility. All right. Bob, can I get a mic? Am I still on? Awesome. Okay, thank you. I'll spend the last maybe 10 minutes or so of my time with you before hopefully we can open it up to discussion and questions and debate. Is why bother doing all this work? What's the motivation for doing this kind of thinking and spending time to learn how to translate climate change to engineering through the lens of risk? Why bother? There's some really great and compelling reasons for doing this, besides just altruism and doing the right thing. In my mind, they cluster into these categories: legal and financial liability, professional engineering standard care, commercial risk or commercial opportunity, if you understand that risk, inverse of risk is opportunity, guidance and regulation, it's fast emerging, and finally, but importantly for especially students on this call, career opportunity, clear career opportunity. So I'm going to touch on these just to give a flavor of why I think it's really pertinent to be thinking about climate change risk and learning about how to translate climate into engineering risk. I'll start with legal and financial liability. This is the thing that would scare you out of all those things. Increasingly, climate change is being invoked in massive class action lawsuits. And these are lawsuits centered around typically individual, very, very damaging extreme events. This is a satellite image of 2018 Camp Fire in California. This was in 2018 the most damaging, most costly climate event in the world, climate disaster in the world at $18-point-something billion, $16-point-something billion, and many lives lost. There is a standing securities action against PG&E, the company that owned the power lines that fell down and started these fires. This is a class action initiated because investors in this public corporation lost billions of dollars when its stock prices collapsed because of this fire. One of the main arguments, I won't get into too many details here because I'm not a lawyer, but one of the main arguments was and is that climate change wasn't considered in the design and operation of the power lines in question here that fell down and sparked this huge, devastating blaze. And so climate change actually plays a really central role in this massive legal action against what is still a very large public corporation. A lot of the systems in question were engineered systems, and so there's no doubt that buried in this effort, there are engineers on all sides of the equation in this very big lawsuit. There's similar things closer to home. I'm blurring out this because I don't want to get into details of places or things like that. That's not the point here. The point here is to note that when engineered systems fail, especially due to extreme weather events, and there's some tie between those event change, then one course of action that damaged plaintiffs take is to invoke climate change as not being considered in the design of the piece of structure. So engineering comes into play in terms of legal liability for the engineer and the designing engineer's employer, and also financial liability for insurance and payout and all sorts of stuff like this. So it's very, very much an emerging driver of legal action. It's financial costs. This is a plot of trade losses over time. In Canada, the costs are going up and up, and in many cases, this is due to very damaging natural disasters, which can have ties to climate change in terms of their likelihood of occurrence. We talked about earlier. And so, again, many of these damages occur to engineered infrastructure, which brings engineers into this legal and financial framework in terms of considering climate change risk. That ties really closely to engineers' standard of care. These are quotes directly out of, and I know from experience because I'm studying this book right now from a professional exam, geoscience exam. These are quotes that define an assessment of whether an engineer's standard of care was met, or conversely, whether the engineer was negligent in their actions or their design. So again, this is kind of a scary thing, but you can avoid it considering climate change. Here's some quotes. What would a reasonable person do under the circumstances? Professionals are expected to use reasonable care, best practices, and well-tested principles. A reasonable person now understands that climate change is happening and may impact long-lived infrastructure. That's why Engineers Canada, for example, in their Principles of Climate Change Adaptation for Engineers, states pretty explicitly, and in many places, that historical climate trends cannot be simply projected into the future as a basis for engineering work. So there's a clear, in my mind, a clear paradigm here emerging where engineers' standard of care now, by default, includes consideration of climate change instead of only as an option. Lots of guidance and regulation is emerging that's really well aligned with legal and financial liability and standard of care. Climate Lens is a great example. A website for Climate Lens is pasted below, and I really encourage folks to go and take a look at that, especially in terms of resilience assessment, which is a gateway that municipalities and other organizations wishing to get money from Infrastructure Canada, lots of money, to build big, expensive, long-lived infrastructure. They have to pass through a resilience assessment to get that cash to build their project. And what that resilience assessment is, in principle, is a climate change risk assessment, followed by an assessment of any adaptation actions that be necessary. So this is now mandatory for all big Infrastructure Canada funded infrastructure projects, and it's pushed out across the country. Now it's mandatory. Website screenshot is on the right. It's evergreen, but folks should definitely go there and get familiar, I think, with Climate Lens as a real great example of climate change risk assessment in practice. Maybe the other guidance and regulation piece to consider is climate resilient buildings and core public infrastructure project. This is run by National Research Council primarily, I believe. This is very practical. It's to update prominent codes and standards, particularly the National Building Code of Canada and the Canadian Highway Bridge Design Code. So the next iteration of these code updates in something like 2024, 2025 will include, for the first time, very explicit guidance and data associated with bringing climate change, future climate change conditions into infrastructure that's built today. So this is exciting, and this is work that's very much underway across a constellation of groups and teams that, in principle, will come out with codes that explicitly include climate change in their quantitative and qualitative guidance. And finally, commercial risk, but also commercial opportunity. I like this quote from Mark Carney, who is the former head of the Bank of Canada and the Bank of England, and now the UN Special Envoy for Collection and Finance. He's financial. This quote is, "Companies that don't adapt will go bankrupt without question." And this quote is in relation to efforts that he and others are undertaking to develop guidance around climate risk assessment for commercial purposes and corporate purposes. And they're really embodied in this recommendations of the Task Force on Climate-Related Financial Disclosures. Hugely important document and an important consideration, again, that engineers often may get themselves into as not just engineers in the company, but sometimes owners of companies. Last but not least, opportunity. 5 minutes on Google, you'll find you a whole bunch of very interesting job ads. These are live job ads, by the way. I scrounged them last week, and they're not endorsements. I should also add that. It's a Government of Canada employee. Fascinating job ads, fascinating job titles from some of the biggest and most prominent engineering companies in Canada and in the world. I personally like the middle title the best, Senior Climate Risk Engineer. If there's 3 words that capture the point of my talk, it's this job ad: climate, engineer, and in the middle is risk. I think it's a great title. Again, not an endorsement of anything here, but there's career opportunities for folks who are versed in engineering, climate change, the language of risk. Okay, I'm going to close the talk really quickly with something. It's kind of fun, but it's also, I think, kind of practically useful. A couple quotes that I call things that make you go, and you kind of get, if you're practicing climate risk engineer, you may look like Freddie Mercury here when he's posed with this really weird question on, I want to be a millionaire. Things that make you go, statements that make you go, So I'm going to argue that you can address all of these statements pretty well using the language of risk, and I'll show you how. First one, I am adapted to climate change because my design is energy efficient. Okay, well, you can use, first of all, just the first principles of climate adaptation, which is climate mitigation, to clear up the fact that just because your design is energy efficient, doesn't mean it's not vulnerable to climate change impacts. And then you can describe those climate change impacts in terms of risk. And it's a tangible way, parse apart different aspects of this statement that conflate adaptation and mitigation. You can do that using the language of risk. I need some climate data for my project is a great one. Well, the answer to that statement, or the reply to that statement, is what are you already vulnerable to? What kind of environmental conditions tend to keep you up at night? That is going to be the great first step to identifying climate data. It's pertinent and practical to start digging into in more depth. And you do that by identifying which risks the operator, the designer already experiences today. Climate change causes extremes. Well, climate change doesn't cause extremes. It causes extremes to get more intense or more likely, or less intense and less likely. And you can talk about that in terms of risk and changes to risk. The risk of flooding in Toronto has always been present. Climate change just changes that risk profile over time. You can talk about, you can respond to statements like, I'm going to use RCP 8.5 using risk calibrated language. You can say, you can use RCP 8.5 for your design. It might cost you more, but maybe it's a good idea because you're going to be very resilient to impacts. I need a number for some point in time in the future. Again, you can use risk to explain why that number changes over time and why the risk in the near term may be less than the risk in the long term. You can start to frame questions around time frame in terms of risk. And finally, the best question of all, I need this by Friday, and this comes Thursday afternoon. And you can reply with some tempering statements around the fact that climate risk assessments are sometimes a little bit of work and a little bit of effort to carry out effectively. But you can also provide some encouragement because you do know how you can prioritize aspects of that work to get at the most important things first. For example, identifying the most vulnerable system components, and also identifying the climate impacts that you may want to really analyze in depth because they seem to impact a lot of things that the operator or the designer cares about. And you can also keep in the back of your mind that this type of work isn't, in the operational sense, isn't so much climate research as it is climate services or climate service provision. And so there's an aspect there too, to not getting bogged down in the best information, but using what's on hand to provide the best answer possible in a limited time frame. So if I was Freddie Mercury here, I would say that risk assessment gives me answer C, which is it all. It's a great way not to solve problems, but to facilitate conversations that make sense across both sides of the climate change engineering spectrum. Okay, with that, I'll close my talk. So the main points, if you're to take away from this talk at all, climate change is equivalent to changes in risk. So you can talk about climate change in terms of risk changes, and that facilitates a whole bunch of conversations that are hard to have otherwise, because risk management concepts can really effectively translate climate change topics into engineering decisions, thinking around engineering decisions. There's great motivation across a number of dimensions to think about climate change in terms of risk. Those range from regulatory, legal, financial, and professional drivers to understanding this concept of climate change as risk. And these drivers are only growing over time. So with that, I will conclude and welcome any questions or comments in discussion.
Yeah, thanks a lot, Jeremy. Oh, let's turn my video back on here. Thanks a lot. I found that very interesting. So I think the best way for us to do questions, number one, you can just ask them in the chat. I'm pretty sure that participants are able to type things in the chat. So if you have questions, please feel free to put in the chat. Alternatively, if you would prefer to ask it using your voice, I can potentially make it that you can talk, I think. Well, we can try that. So you can put your hand up if you have a comment or a question you prefer to ask with your voice, and then I can make it that you're able to talk. Otherwise, just feel free to put them in the chat. I don't see any questions, but maybe someone's typing a really long and detailed one. Oh, Karen. Okay, first let's here, Karen, I think you should be able to unmute yourself already if you want to put your hand. There you go.
Hi, Jeremy. Thanks so much. That was a great presentation. So I had a question about the Engineers Canada document that you mentioned at the end, where they, say that we shouldn't depend on sort of historical climate data. So in practice, like you've been working, previously working at an engineering firm, like is that taken to heart, or how do people kind of, adapt to that recommendation in practice now?
Great question. I mean, practice is rapidly changing in my view of it anyways, where it's in a really exciting sort of transition period where the level of sophistication is going up really rapidly in the engineering sector. Again, as I've been able to observe it, and I don't have a very long time period there. So, but that being said, there still is lots of work to do. In many cases, climate change, rightly or wrongly, is considered, in terms of a safety factor, things like this. And hey, you know what? In many cases, I think that probably works. It doesn't really capture some subtleties, and it might provide problems either in budgeting, over budgeting of a project, or increased risk that's unintentionally being exposed. It's a tough question, and I think it depends on who's doing the work. I also say that some of the thinking too is important around time frame. I mean, climate change, if you're designing something that's going to last a year, you don't really need to get into climate modeling and all this stuff to deal with that. There's some points where practically I think you don't need to get so wound up about climate change. Even recognizing that spectrum is something that's being developed pretty actively right now. I don't have a very good question for you, but it's great. Good answer, but it's a great question.
All right. Thanks for the first question there, Karen. The next question I see is from Pippa Cookson Hills, and their question is, what argument, legal, financial, etc., would you use to sell climate change services to a client that is skeptical of climate change?
Yeah, great question. I think the climate adaptation side of the equation compared to the climate mitigation side has it easy because you can sell a client on reducing their risk, right? Clients, no one wants increased risk, and in the sense that climate change can be communicated as an increase in risk, you can, quote, sell climate change to them alongside your sale of other risk reduction things that you're providing them. Reduce car accidents in the case of transport infrastructure or whatever, earthquake, seismic, all these other risks. Climate change is just another risk, and people people want the risk reduced, that's just one way to sell it very easily. In my opinion, it becomes a very easy, selfish sell. That puts it cynically.
All right, thanks for that question, Pippa. If you have a follow-up question, feel free to type it in. Oh, no, perfect. She says, great, thanks so much. The next question is from Daniel Posen, V2 number 2, or just Daniel Posen for short. He says, great talk. I'd be curious to hear where you think are the biggest gaps for new research.
Yeah, great question. I would slightly rephrase that question a little bit, and I would ask, what are the biggest climate vulnerabilities and impacts nationwide? And I can give a really glib answer to that: fires, floods, sea level rise, health impacts. There's others for sure, but if you delve into those major risk categories or vulnerabilities, you can pretty quickly find places where the scientific basis in terms of research is lacking. To me, that's the place to focus energy, is on the things, on the low-hanging fruit that makes the biggest difference to addressing, understanding of risks, or the biggest risks in the country or globally or municipally, whatever you're interested in. The gaps in research, I think chasing gaps in places that speak to the biggest vulnerabilities is the way to go. Hydrologic modeling at the national scale, put that out there. Sea level rise, another one, getting that nailed on coastlines. Lots of work to do everywhere, but it can be prioritized, I think.
All right, perfect. The next one is just a comment from Laura Minet. They say, thanks so much for this inspiring talk. The next comment is a question from Ariana Miranda. And the question is, what do you think is the greatest contributor to climate change?
Good question. You can go back to kind of some of the IPCC, for example, things like this that partition out at the global scale. And I think even in Canada's Changing Climate Report at the Canadian scale, what are the biggest drivers behind change that we're seeing now? One of the biggest ones is, of course, radiatively active gases in the atmosphere, CO2, CH4, nitrous oxide, things like that. Land use change is important too. But to answer that question really authoritatively, you can turn to great reports like CCCR 2019 or IPCC stuff.
Excellent, thank you. The next question is from Paul Kushner. Does the climate lens focus on risk, or are opportunities also part of the analysis? For example, opportunities to shift resources away from areas of diminished risk under climate change.
The climate lens is interesting in that it focuses on individual infrastructure projects. So it's specific to funding applications to build specific pieces of big infrastructure. So I'm not sure it has the scope, as I understand it, to shift resources from one sector to another, this kind of thing. That's maybe the purview of higher level sort of assessments. But it does, I'm pretty sure it does indicate in its guidance that you shouldn't only consider risks, but you should consider opportunities. For example, warmer winters mean it's an opportunity to maybe in the future swap out your giant winter heating boiler in your building with a smaller one. And so that's an opportunity that can manifest at the individual infrastructure level. And I think Climate Lens does specify that you need to look for that stuff where you can.
Excellent, thank you. The next question is from LA or from La. Great talk. What is your suggestion on how to deal with higher order effects, for example, wildfires and related changes in debris flow, flood hazards? From Lucas Arson.
Yeah, I mean, how to deal with effects. That's where engineering is so critical in my climate view of things, is dealing with these effects. In other words, developing actions that reduce the consequences of these effects, if you want to speak risk language. The how around there is is something that engineers have a huge place in answering on a case-by-case basis. So there's not a blanket effect that can fix wildfire and debris flows, for example, in one fell swoop. Depends on where you're at, depends on the characteristics of the risk that you're facing. So there's not really an answer that I can provide there, the blanket statement, but the blanket statement I can provide is that engineers have a huge role to play in understanding that how question and actually implementing it in design, which is super cool.
Excellent, thank you. And then this will be our last question because it is 6:32 Eastern time. On your risk chart, from Sherry Ann Ram, she asks, on your risk chart, climate action was on the top right corner. Are you able to specify a few climate actions in your estimation that we can take that would have the largest impact to reduce GHG emissions?
Yeah, good question. I mean, something I have to try and think about personally, and probably everyone should. There's great work out there, and I think a Google search will give you some great rankings of actions. In Canada, you can be specific to Canada. Of course, driving your vehicle less, eating less greenhouse gas intensive food sources, beef. That's one. But one that surprised me recently was just building heating. I think is possible. Don't quote me here, but I think it's right up there, if not the top emitter of greenhouse gases in the country. Winter heating, and so building efficiency is a huge thing. As another example, good question for sure. It's important to figure those priorities out at the personal and the organizational level, national level.
All right. Well, thanks everyone for your questions. If you are interested, I just put the CSE's website into the chat. My plan will be to follow up with people who did register for this presentation for future communications, and to maybe get some feedback on how this presentation went in the organization. And if you didn't register, you can share your email with us. I think there's an email list sign up page on our website if you want to check it out. Other than that, thanks everyone for coming. Thank you, Jeremy, for the presentation. It was great. Good job. And that's it. So everyone have yourself a good evening or day or whatever time it is where you are. All right.
Thanks, everybody.
Bye, everybody.